Welcome back, everybody. So let's continue. I rewinded because the question during the break, where were we? Yes, we were here. So if I recap, basically, if I give you a table with a certain number of columns and rows and contents, and I give you a functional dependency with a few attributes on the left, a few attributes on the right, then I can ask you a yes-no question. Does this table fulfill the functional dependency? That's a yes or a no. I dream of seeing that in Who Wants to Be a Millionaire, right? You see the last question for 1 million francs, like here's a table, which one of these four functional dependencies is fulfilled? Who feels comfortable enough to answer this correctly? If I give you a table and a functional dependency, who is able to tell me yes, no? Very good, okay. So again, the intuition, and that's the reason it's called functional, is that DE, what is in DE, is a function of what is in AB, right? So I could basically take DE out of the table and give you the function instead, and knowing A and B is enough, right? Okay. So another way to putting it is that if I play a game with you and I give you the table, and I tell you, here's the value of A and B, can you tell me the value of D and E? Well, if you have a functional dependency, the answer is yes. You can always tell me the value of D and E, right? That's basically dependency. So here's coming back to our previous example. We here have a functional dependency because price is functionally dependent on product. Who agrees? Yeah, okay. So now we have a formal name for that. I explained intuitively when I give you the example of the web shop that all phones have the same price and so on. But now I can use the fancy wording that we've just learned and say that price is functionally dependent on product, right? Now, if you look at the notation here, product, it's inside quotes, and there's the curly braces for the set and so on, becomes very cumbersome when you keep writing all over the place functional dependencies, especially in exercises. So we simplify a little bit. And basically what we do is that we drop the curly braces, we drop the commas, and we just write like AB functionally determines DE, right? So it's just a matter of convenience that we do this. But you should always remember that when you see this, the big font here, it's really the set of attributes containing A and B and the set of attributes containing D and E. But it's very convenient. You don't even need the spaces. You can directly write AB without any space. That's fine too, right? In exercises, at least if you use letters. Okay. So typically, that's what we do. I basically directly write a product, a row price, and that's it, right? That's more convenience. Okay. Do you agree that if I now look at a different functional dependency, namely price functionally determines customer, or customer functionally depends on price, do you agree it does not hold? And what's nice is that if I want to show you it doesn't hold, that's very easy. All I need is a counterexample. Right? You know, in mathematics, when you have this for all, if you want to prove that for all is true, so for all tuples that match on price, they have to match on customer, that's a very tough proof. But if I want to show you that this for all does not hold, it's easy. You just find a counterexample. You find one that's enough to destroy the whole thing. So if I want to prove that price functionally determines customer doesn't hold, I just need a counterexample, and it's right there in red. I have two tuples who agree on price, but they disagree on customer. That's enough to prove that the functional dependency is broken, right? So it doesn't. Okay. All right. Now this is an equivalent characterization. I don't really know if it helps. So for some of you, it might help. For some of you, it might scare you even more. If it scares you even more, just forget about it. But let me still show you. There is an equivalent way of showing that there is this. So basically, the idea is that if you pick a specific values that A, B, and C could have, that's basically what we call F here. So F is just a specific record or part of a record that attributes values to A, B, and C, right? So for example, F could be price is 2000. Then if I select the tuples that have this value, I would basically get these two records in here if I select on price is 2000. So if I select and then I project to the attributes that I want to see if they match. So here I would take these two, then project to customer. Then if I have a functional dependency, what I should get after this selection and this projection is either a single value or nothing, right? Now you see in that case, if I do it here, if I select on a specific value of the price, for example, 2000, and then I project on customer, I get two values, John and Mary, right? So it means the functional dependency doesn't hold. It has to be just one value or nothing. Let's do it on product and price. So this one does hold. So normally, if I do the same here, I should get either 1 or 2 or 0. So let's say I take product equals phone as an example for F. So I'm looking for the tuples for which the product is phone. They should have all the same price. So let me do the selection. So I select on the products that have this value. Now they all have the same value. And now I project on the price. Why the price? Because that's the right-hand side here. And then, of course, I have to eliminate duplicates. Bingo, just one value. If that's always the case, whatever you put in there, not just the phone, but anything else, it's always one value if it is on the table. Of course, if you pick a value that is not in the table, it will be empty. It has to be 1 or 0. If it's 1 or 0, then the functional dependency works. Does it make sense? Right? It really has to do with the fact that when you apply a function, that should give you one value, right? Not several. Okay. All right. So I'm just repeating what I've just said. If you want to say it with natural words, you're basically saying that T is a function of S, essentially, when S gives you T. Yes? For example, you have a sale in cars. You have a? Yes, absolutely. But basically, the point you're making is this is bad design, right? Because with this, you cannot do a sale. So you're making an excellent point. And if you design it right, then you can do a sale. If you split it nicely into tables and so on, then that gives you the means. Yeah. So again, the answer to your question is what I'm showing to you is very bad design. But what I'm doing here is showing you why it's bad design. This is what I'm showing. I'm not there yet. So the functional dependency, we'll use it later in the normal forms. And then you will understand how we mathematically show that it's bad design. Yeah. So you should not do a web shop like this, right? If you do a web shop, it's a very bad idea. Okay. Oh, I just recollected. I need to tell you there was a question before the break on whether in this where in it's allowed to have multiple values. Apparently, it's not in the documentation. So you really have to compare a single value, and the select from where must have exactly one column. If you want to test on several values, you need to use a construct that exists, basically. There is an exists clause, and then you can test for the existence of a record that has the specified value in the nested column. So that would be the answer to your question. It's a bit more involved than simply using in that case. Yeah. Does it address the question you had? All right. Okay. So if that helps, that's good. If that didn't help, forget about it, right? This was just yet another attempt to characterize. But what I find, again, the most intuitive is to just say that some attributes are a function of some other attributes, given a table. That's, for me, the most intuitive way of saying that. So here we would say that the price is a function of the product, right? You could call it P. So P of phone is 800, P of laptop is 2000, P of HDTV is 1000. But of course, it only works if you have a functional dependency, right? And that would be mathematically the function. Okay. Who is comfortable with functional dependencies? Okay, on Zoom, can we see a few raised hands on Zoom? Who is comfortable with functional dependencies? Very, very good. Okay. So then we'll move on to some other scary concept. It's actually great that we do it on Halloween. Super keys. What is a super key? Well, it's a set of attributes first that can or cannot be a super key. So here's the scary definition. So I always have my relational table. I have a set of attributes. Subsets, of course, they have to be in the attributes of R for this to make sense. So this is why we say a subset. Could be ABC, for example. Then we say that the set of attributes, K, is a super key if the following functional dependency holds. Key functionally determines everything. Then it's a super key. So basically, for example, here I replace K with ABC. It's just easier if you actually instantiate it with actual names. So a set ABC of the attributes, some attributes of R, is a super key if whenever you take two random tuples in the table, if these tuples agree on the super key, then they are the same tuple. You cannot have two tuples that are different and that agree on the super key. If they agree on the super key, it's then it's the same tuple. Okay? So it means that in order to know if two tuples are the same, it's enough to check if they match on the super key. That's why it's called super. Right. All right, so here's an example. Can you give me a super key? Just like out of the blue. So I'm basically looking for a set of attributes that functionally determines everything. If I know the values for these attributes, then I know the tuple. Anybody? Let me tell you what's not a super key then maybe. So the category is not a super key. This here. This is not a super key. Why? For example, I could say category high tech, but there's two tuples with high tech. So if I just say category high tech, that's not enough to identify the tuple. So category is not a super key. So what is a super key? Yes? Product. Yes, absolutely. Product is a super key. How do you see it? It's all different values in there. So if I tell you product is phone, then you know that this is the one. There's only one tuple that does that. If I say a product is a 4K TV, that's the only one, right? So indeed, it is absolutely correct that product, it's a singleton set of attributes, only has one. Product is a super key. Do we have a question on Zoom?
What's the difference between super key and primary key?
I'm going to get to this. A primary key has to be a super key, but the contrary is not true. You could have a super key that's not the primary key.
I've also got a question.
So I didn't hear that.
So if integer would be not 10 and 10 in the first row and the second to last row, maybe like 10 and 8, would it be a super key as well because it differs? Or is it just like because I know the product, I know everything else?
You are correct. So if you replace this 10 right here with an 8, for example, then it is true that stock would be a super key of the table. However, that is what we would call an accidental super key. It's just because at some point in time, by accident, it turns out that all of the products have a different quantity, but it's not meaningful. It's just an accident. It's just by chance that at some point it's a super key. But that I will come back to it very, very soon. But you're absolutely correct. As it is mathematically, if you forget about what it means, mathematically, it's not a super key because 10, for example, wouldn't uniquely identify a tuple. It would become a super key if you replaced it with a value that is not anywhere else. You're absolutely correct, right? This is the reason, by the way, why it would be a very bad idea to make stock a primary key, right? We don't want that. That would make any sense in a web shop. Do you agree?
Yes, thank you.
Yeah, all right. Thank you very much. All right. Let me ask you something else that might also point to the primary key question. If I give you now the set of two attributes, product and price, these two attributes, is the set of two attributes, product, price, a super key? Yes or no? Who thinks yes? See 4 raised hands, 5 raised hands on Zoom also. Who says no? I don't see any raised hands. Indeed, it is the case that product price is a super key. It is absolutely correct. How do I see it? Like, for example, if I tell you the product is laptop and the price is 2,000, can you identify the tuple? Yes, absolutely. That's the second one. Right. In fact, you probably now discovered kind of a mini theorem. If I take a super key and I add more attributes, then it's still a super key. I'm just giving you even more information, right? So if you're already able to identify a tuple just with the price, then if I give you even more information than the price, sorry, with the product, if you're able to identify a tuple with the product name, and on top of that, I also give you the price, then you're still able to identify the product, right? Because I just give you more information. For whom is that clear? All right. So in fact, product price category is also a super key, product stock is also a super key, product category is also a super key, product price category stock is also a super key, right? So we have plenty of super keys. And now coming back to your question, you do realize that in all these super keys that I gave to you, many of them don't make sense as a primary key, right? Product might make sense, but product and price together, it doesn't make sense to make it a primary key, right? So that should also address your question. But I'm coming to this, right? I have slides on the relationship between super keys and primary keys. Okay. So this is a super key that we all agree on. This is also a super key. If I keep adding stuff in there, I still have a super key. This is also a super key. This is not a super key. Why? I just need a counterexample. So price, if I tell you the price is 800, then you cannot tell me what tuple it is. Could be the first one, could be the third one. So it is not true that price functionally determines everything, right? So that's not a super key. That's also not a super key. The category alone is not enough. High tech is ambiguous, entertainment is ambiguous, not a super key. This is not a super key, right? Because the 10, for example, wouldn't suffice. This is a super key. In fact, that's a theorem. If you take the set of all attributes of the relation of the table, the set of all attributes is always a super key. It's very intuitive, right? If I tell you all the values of a tuple, then you know what tuple it is, because it's a set. So there's no duplicates. So theorem number one, the set of all attributes in a table is always a super key. Who agrees it's easy to show? Very good. So it means that in particular, there's always at least one super key. Just take the set of all attributes. Theorem number two. So here it's basically the mathematicians love these sort of things. It's not very useful in practice, but it's like the vector space with dimension 0 or that kind of stuff, but still mathematically it has to work, right? So what if we take an empty table? There's absolutely no tuples in there, completely empty. Then in fact, if you plug in the definition, anything is a super key, right? Because there's no tuple at all. So you don't even have any tuples to identify. So then it's always a super key. If you take a table that only has one record, then it's also the case that any set of attributes is a super key, right? Because you're asking, can you identify the tuple? Well, there's only one tuple. So of course you can identify the tuple. I don't even need to give you anything. So that's also a theorem. If the table only has one record, then any set of attributes is a super key. Who agrees? Right? Okay. Now let's take a table with just one attribute, only one attribute and at least two records. Then there is only one super key, and that's this attribute as a singleton. Who agrees? Okay. Again, these are really corner cases because in practice, you won't often have an empty table or a table with just one attribute. But again, when you do something formally, the mathematicians like to make sure to sweep in all corners and to check that it's also working on the special values. Now, this theorem is actually interesting because it's actually practical. When you have a table that is interesting enough, meaning it at least has two records, then the way you locate the super keys is you find attributes such that two tuples will always differ on these attributes, right? So for example, if you take, let's say, phone and laptop, or the product, if you take any two tuples, then they will differ on it, right? If something, however, is not a super key, like that would be the case of entertainment and entertainment, then here you found two tuples that do not differ on the category. So it means category is not a super key. So again, the intuition for finding a super key is you try to find the attributes that are able to discriminate between tuples, to tell them apart. Right. If the attributes are not able to tell tuples apart, then it's not a super key. Okay. So far, so good, everybody? So now you know what a functional dependency is, you know what a super key is, and now you notice that a super key is defined in terms of functional dependency, right? Super key is basically, it means that there's a functional dependency from that super key to all attributes. So we are building a pyramid like this of concepts. Okay. The next thing I'm going to do is I defined the concept of functional dependency and the concept of super key on one table. I said I'm giving you one table and I'm asking, is this functional dependency fulfilled? Is this a super key of the table? What if now I don't give you a table, but I give you a table universe, meaning not just the table at a point in time, but all tables that you would accept in your web shop or in your database, right? Well, it turns out we can extend the definition of both of these things, of functional dependencies and super keys. We basically say that a functional dependency or a super key holds on a universe of table if it holds for every table in that universe. That's basically, it's a very simple definition, right? So you can now say that the functional dependency S determines T holds for a table universe if it holds for the entire universe. So this is why you can see it as a constraint, right? So S functionally determines T is a constraint of your universe because all the tables in that universe must agree with that functional dependency. The super key is the same. You basically say that a set of attributes is a super key of the universe if it's always a super key of any table in that universe, right? And again, that's something you enforce in your universe. Okay. I redid the same slide, but instantiating S and T as actual sets. So I'm replacing S with ABC and T with DE. Of course, 3 and 2 are totally arbitrary. It could be any number of attributes. But basically, I'm saying that, for example, if I have a table universe, that ABC functionally determines DE holds for my table universe if it holds for any table in that universe. So any table in that universe, DE would be a function of ABC. I could say that ABC is a super key of my table universe if it's a super key of all the table in the universe. It means that for any table, ABC determines everything. If you know the value of A, B, and C, then you know the tuple. Who is with me? All right. So there's no new concept in there. It's still functional dependency super key, but now I'm able to also define them on a universe of tables and not just on a single table. Okay. And the reason I'm telling you that is to issue a big warning, but in fact, I don't need to do it because one of your colleagues on Zoom already did it, and they were actually completely correct on that. Look at the stock. This is probably what you meant on Zoom earlier. In that case, imagine I have a universe of tables. That's my web shop, badly designed, but that's what it is. And earlier, if I look earlier what I had here, stock was not a super key, right? But imagine that some people place orders and now somebody bought a 4K TV and there's only 9 left, right? That's fine, right? It's a web shop, people buy stuff. So now I remove 1 to 4K TV and I have 9 left. Now you notice what happens. Stock now is a super key of that table, But do you agree it's not a super key of the entire universe? Because that's not always true. It's an accident. It turns out to be true now, but tomorrow, if I buy 1 more 4K TV in my inventory, that will again no longer be a super key. So this is a case where you might have by accident a set of attributes that is a super key at a certain point in time for a specific table, but it's not true at all times. It's not true for the entire universe. Who sees that? All right. So this is something to be very careful about because this is one of the tricky points. So you have to be careful with these things. And the reason you need to be careful is this. Imagine that these are 3 snapshots in time of my web shop, 3 different points in time. You can see that at that point in time, it's not a super key. There's 5 of each TV. At that point in time, somebody purchased 3 4K TVs. So now it's a super key by accident. And now what happened? Somebody else bought 3 HD TVs. So now it's again not a super key anymore, right? So you see that there's some fluctuations here, yeah, right? Sometimes it is, sometimes it is not. Yeah, that's I think what I love this word in Auschwitz. I think it's called the potato-early, when something sometimes works, sometimes doesn't work. So stock is a potato-early here. It's sometimes a super key, sometimes not a super key. And of course, for the entire universe, so that would be the universe of all the tables for my web shop forever, right? Any content, then stock is generally not a super key, even though by accident, sometimes it might be one. For whom is that clear? All right, I really insist on that even more than in previous years, because this is often a point of confusion. So this is why you need to be careful if you're talking about a single table or a universe. Now, from a very practical perspective, and here I'm talking about the exam and exercises, when we ask if something is a functional dependency or super key, we cannot seriously give you a universe at the exam. We are not going to give you 1,000 tables and then ask, is that a super key of that universe? That doesn't make any sense. So what we do at the exam is that we give you one table. Then we ask, is that a super key of that table? But what we try to do is, at the exam, we will avoid giving you something like this. We will basically try to be careful not to have accidental super keys in there. So we might give you this table, we might give you this table, and we are going to be careful to not give you tables with accidents. So what we basically say is that the table is a good representative of the universe, meaning that it kind of has all the functional dependencies and super keys that the actual universe has. And that allows you to focus on that one table, right? Without worrying on accidental dependencies and super keys. Okay? And typically, I think when we do that, we say at the exam, we add a hint, we say you can safely assume that this table is representative of the universe. That's what we tell you. Okay. Which brings us to candidate keys. And again, candidate keys must be explained having what I just showed you here in mind. Candidate keys. So candidate keys are halfway to primary keys, right? I'm going to link super keys to primary keys, but in order to link the super keys to the primary keys, I need candidate keys. So the idea is that some of the super keys are candidate keys, and one of the candidate keys is the primary key. That's basically the relationship. So let's go halfway to the candidate keys. A candidate key is a minimal super key. That's the easy way to say it. But now if I write it formally, then I have some table universe, preferably a universe. And I consider a set of attributes, K. I think I intended to replace K with ABC, but I forgot to do it. It should be the same thing. So given a subset ABC of attributes of U, ABC, blah, 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 is a candidate key if it's a minimal super key. What do I mean with minimal super key? What I mean with minimal super key is you cannot remove any attributes. Minimal in that sense. So if ABC is a candidate key, if you remove A, for example, and you just have BC, then BC cannot be a super key anymore, right? If you remove A and BC is still a super key, then it's not minimal because you can remove A. So that's what it means. So it means that it's a candidate key if none of its strict subsets is a super key. If you remove anything, it's no longer a super key. For whom is that clear? The reason I'm insisting on that is that there's a mistake that some people do on minimal. Some people understand minimal in terms of the number of attributes. So basically they say there are super keys with 3 attributes, there are super keys with 2 attributes, and you look for the minimal number of attributes in there. So if there's a super key with 2 attributes, then it's a candidate key, and all the super keys with 3 attributes are not, because 3 is not minimal. But this is wrong. This is not what minimal means. Minimal really means in terms of subsets that you cannot remove attributes. If there's any mathematician in here, it has to do with lattices, the algebraic structure, but I don't want to scare you with that. So a candidate key is a super key if all the attributes are really important. You cannot remove anything. So let's do it on this example. So we have a table. I'm assuming it's representative of the universe. That's basically the warning I gave you. So do you agree that AB is a super key? How do I know? Because AB functionally determines C, right? It functionally determines everything. It just suffices to look at what there is in there, AB, AC, BC, the contents. So let me show. This, and this are all different. So that's how I know it's a super key. So these two are a super key. Do you agree BC is also a super key? If I say, for example, C2, then I know this is the tuple. If I say B1, then this is it. If I say C1, then this is it. So it's also a super key. AC is also a super key. If I say A1, then I know we are here. If I say A2, I know we are here. If I say B1, I know we are here. So it's also a super key. You remember that if I add attribute, it continues to be a super key. So it means that ABC is also a super key, right? It's even larger. So in fact, we know by the theorem that the set of all attributes is always a super key. So these are all super keys. But if you look at them, what you notice is that some of these super keys are subsets of some others. Basically, AB, BC, and AC are subsets of ABC, strict subsets. So what we do is we remove all of the ones that are the superset. So ABC goes away. Why? Because I can remove A, and that's still a super key. I can remove B, it's still a super key, right? So this is why I'm getting rid of it. It's not minimal. So I'm getting rid of this one, and only ABC, AB, BC, and AC are considered minimal, right? ABC is a super key, but it's not a minimal super key. It's not a candidate key. But I still need to explain why AB is minimal, right? How do I know AB is minimal? Well, I need to try to remove B or to try to remove A and see what happens. So let's see I remove A. Is A a super key? Why? Yes, you can see A is not a super key. What about removing this one? What about B? Is B a super key? No, because you can see here, it has an ambiguity. So basically taking AB, I try to remove A, I try to remove B, but it stops to be a super key. So it means I need A and I need B. So this is why AB is a candidate key. I can do the same here. If I remove B and look at only C, C is not a super key. So I cannot remove B, I cannot remove C, they're all necessary. So BC is a candidate key. Same here, I can remove A, I can remove C, but then it's no longer a super key. So they're both necessary. This one, I remove A, it's still a super key. So A is useless, right? I can just have B or C. Or I can remove B, it's also useless if I keep A and C. And this one also continues to be a super key. So this is why this is not a candidate super key. It's not minimal. It has unnecessary attributes. For whom is that here? Very good. Can you give me a few candidate keys in here? So for example, we said that the set of all attributes is a super key, right? So if you take product, price, category, and stock, all of that, that's a super key, right? But is it minimal? It's not minimal, right? Because product in itself is a super key too. So if you take all attributes, you can remove price, remove category, remove stock. You're left with just product, and it's still a super key. So it means that the set of all four attributes is not a candidate key, right? Can you give me other candidate keys? Anybody? So for example, you agree this one is a super key and it's also a candidate key, right? You cannot remove anything, it would be empty and then it's not enough. This is a super key, but it's not a candidate key because you can remove price. This is a super key that's not a candidate key. This is a super key that's not a candidate key. This is not a super key. This is not a super key. This is not a super key, right? How do I know? Well, I actually made sure. You see these two here. They agree on these three values. You have twice the same thing here. That's why it's not a super key. Not a super key, not a super key, not a super key. So in fact, in that case, that's normally the only one, if I made it correctly. Okay. So I saw a few heads like this. Can you give me another candidate key? No, you're correct. That's normally the only one. Okay. In that case, of course. But just so you know, in general, a candidate key is not unique, right? This is an example. The example I gave you here, we have an example of 3 candidate keys, right? So always keep in mind the candidate key is not unique. There might be multiple ones. Okay, so what's next? So here, yeah, so that's a super key that's not a candidate key because I can remove price and it's still a super key. Okay. So here's a theorem. I'm giving you a few theorems. The first theorem is that if I give you a table or a table universe, there will always be at least one candidate key. It cannot be that there is none. How do you prove that? Set, yes, absolutely. It's always a set. Exactly. Yeah, so let me repeat your reasoning. That's exactly the right reasoning. You basically start your proof with using a previous theorem that if you take the set of all attributes, that's a super key, right? Product, price, category, stock. So all attributes together, that's a super key. So you always have a super key. Now, what you can do is take that super key and you remove the attributes one by one. You remove them. Maybe it's still a super key. You remove one, it's still a super key. You remove one, it's still a super key. At some point, it has to stop being a super key. At some point, you will break the super key property if you remove enough attributes. How do I know that? I basically go all the way. Imagine that I prove that it's absurd. Imagine that I keep removing attributes, but it's always a super key. If I remove the attributes and always remove and remove and remove, then at some point I'm out of attributes, right? At some point I remove them all, right? But what happens if I remove them all? If I remove them all, then it's the empty set, right? And if there's at least two records, then the empty set cannot be a super key. So it means that somewhere in between, at some point, if I remove some attribute, at some point it has to stop being a super key, right? So this is why I have the guarantee that at some point I get a candidate key. As soon as I can no longer remove any attribute, I have a candidate key. Who agrees? So there's always, always, always at least one candidate key. Then there's the mathematician's case. If the relational table is empty, then the only candidate key is the empty set. Like, who cares? But still, mathematically, it has to be said. If the relational table has only one row, then the only candidate key is the empty set. How do you say no? Because there's only one tuple, so identifying tuples is trivial. You know what tuple it is, so you don't need any attributes. Another theorem is that if a relational table has exactly one attribute, just one column, and at least two rows, then that attribute as a singleton is the only candidate key. Okay, that's also a mini theorem. Okay. Which brings me to primary keys. And now I will answer the question that was asked on Zoom. The primary key is basically one of the candidate keys. Which one? Well, you choose. That's basically the designer. If you do your job, you basically design your database and so on. You find the super keys of your relational universe. You find the candidate keys of your relational universe, and maybe you're left with two candidate keys. Well, then you have to make a choice. Either you pick this one or you pick the other one. How do you make the choice? Well, it's common sense. You really have to think in real life, what is the most meaningful candidate key in real life? And typically what happens in reality, for example, if you have a database of people, then you're going to use the AHFAO, the social security number. If you have a database of product, you're going to use some reference number of the products. If you have a database, a table of courses at ETH, then you're using the course unit codes. You know that they have codes at ETH. So it's really the choice of the primary key among the candidate keys is not something that the math can tell you. All the math can do is tell you these are the candidate keys, but then it's your choice as a human to pick the one you'd like as a primary key. Okay? So a primary key is just a human choice that you made a choice. This is the candidate key I prefer, and then you make it the primary key. How do you make it the primary key? Well, in PostgreSQL, you write create table, blah, 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 and you add primary key in front of the one you want. Or you write primary key at the end if you want a compound primary key with multiple columns. Okay? So for example, that's a typical thing in real life. You typically would have a product ID in here that you would add. So that's a table. I shouldn't have called it sales. I should have called it inventory. Maybe that's an inventory of my products. And typically you give them IDs like 1, 2, 3, 4, 5, 6. These are just references. For whom does that make sense? Don't see any raised hands. Okay, very good. What is very common, by the way, that you'd see in practice is that it's very common to call the primary key, if it's only one column, something ID. like PID for product ID, CID for customer ID, course ID, CID, university ID, UID. So it's this is something that the database schema designers love to do, basically use this something ID ways of identifying, giving the column name, basically. That's another example, customer ID or CID if you want. That's yet another example. So that's a case actually where if you look closely, first name, last name is also a candidate key in that case. It's not true generally. There can be multiple people with the first name and last name, but in that table, accidentally, you have first name, last name that is a candidate key. Who agrees? So I'm basically left with either first name, last name, or customer ID. As the human being, I think that customer ID makes more sense. So this is the one I pick as my primary key. Okay. And so what we do, so this is what you find in database textbooks, is that, so the super keys are basically sets of attributes. Then you filter out your candidate keys. As I said, there's only two survivors, customer ID, first name, last name. Then you decide customer ID is more meaningful. And what you will find in textbooks is that you underline the attributes that are in your primary key. So you basically say, this is my table schema with just the names of the columns. You could also add the domains, but this is my schema. And you underline the one or more attributes that are in your primary key. That's a common notation. All right? No, that's not today. You had enough for today. I'll keep the prime attributes for next week. So what did we see today? We saw the functional dependencies, the super keys, the candidate keys, the choice of the primary key, the notation, underline. So normally, with what I taught you today, if I give you tables, you should be able to give me the super keys and the candidate keys. If I give you tables and functional dependencies, you should be able to tell me yes, no, that table fulfills that functional dependency or not. So that's what you should be able to do now. Okay. So next week, I'll continue to build on that, and I'll show you the Boyce Code normal form, and maybe if we have time, some of the other normal forms, which will then give you the characterization of a good way to design your tables and your schemas in real life. So now just checking if you want me to accelerate or slow down. Okay, that looks about right. So I'll keep the rhythm. Of course, there's always the textbook with the chapter to read. So it's a good idea to read it. It's explained in a different way, but that gives you another angle. And of course, you should do the exercises, because this is the sort of questions we love to have in the exam, testing super keys, functional dependencies, and so on. So that usually pops up in the exams. Okay, so thank you very much, everybody, for attending today. I hope you enjoyed it. Enjoy the exercises that the TAs prepared for you. Do not forget to use SQL all you can. Fill your textbook, your notebook with SQL queries and make sure that you master it. You'll have PostgreSQL at the exam. We'll ask you to write queries in SQL. So make absolutely sure you master SQL completely. Thank you very much. See you next week at 10 a.m.